Um, we learned about dihydrogen monoxide. That's for diatomic molecular compounds, but this can also be named as an acid. What is its acid name? And so first, when we're trying to name an acid, what do we look at first? We look at the second part. What would that be called?
Oxide.
Yeah. So if we were to imagine this as being an acid like this, then it would be the oxide. And so what do we do when we have an "ide" ending? We put the hydro, right? Because in "ide," with an "ite," it would just be the "aus" ending, but this is going to be hydro, and then we're going to change the hydroxic. Yeah. And so it's kind of funny. So we're probably not going to call it hydroxic. We'll probably just call it hydroxic acid. Hydroxic acid. Although that sounds a little bit funny. Let's see if there are any hoaxes on hydroxic acid or anything like that. I think they changed the name even more. Wiki web. Well, there's lots of ways we could name it. The other name is, hydrogen oxide, like this, or we could think of it as being hydrogen ion and hydroxide ion. So hydrogen hydroxide. If this were hydroxide, what would we name it? We would name it something else. If this were hydroxide, we would name this acid the name wouldn't be so great. It would be hydro. Well, I don't know.
But water is not acid, is it?
Water is very interesting. Water is an acid.
It?
Yeah. But water is a very funny substance because it's also the opposite. It's also a base. It's both an acid and a base. Interestingly enough. But it's neutral. Normally when we think of water, it's neither acidic nor basic, but in chemical reactions, it'll react as an acid or it'll react as a base. Well, anyway, this is, let's see what this does. When it comes to water, this is just some website, hydrogen hydroxide, I don't know. Let's see what else they have. Hydroxylic acid. Maybe there is some hydroxic acid in there. Hydroxic acid. So we got redirected to, I typed in hydroxic acid. This is a medical dictionary. We got redirected to water. And so you could start talking about hydroxic acid, the dangers of hydroxic acid, if you want. But I like to consume hydroxic acid myself. It's one of my favorite.
There's a lot of hydroxic acid around.
Yeah, there is. Anyway, let's go back to this.
Rust metal.
So obviously there's a problem with this. Did we fix it? How did you fix it? People do this all the time. They confuse moles with molecules. Most molecules are not the same thing. Right? So obviously here, so this is got to be spelled out molecules. And then 1 mole contains an Avogadro's worth molecules. And then here's, what do we call this loss conversion factor here? Well, what is that called? The molar mass.
All the software changes are required.
You're right. I can't do it. All right, the next section, turn this on. The next section deals with percentage by mass composition. We already talked about this. If we're interested in percent A, then we need to know how many grams of A, how many pounds of A, how many ounces of A we have, and the total number of pounds, grams, or ounces. And so we just take the ratio and then times 100%. So it depends on how many components. This would be component A. Component A could vary. Sometimes we're just interested in nitrogen. How much nitrogen. Like the chlorinating solution. In the chlorinating solution, all they cared about was how much chlorine was in that mixture. It's a chlorine atoms. In that case, we hear chlorine. But sometimes we're interested in how much of particular compounds there are. So, for example, if you're looking at oil, like oil of pine, something like that, from a tree, which is a mixture, maybe we're not interested in how much carbon there is, how much nitrogen there is. Maybe we're more interested in how much of a particular compounds there are in there. And so sometimes we'll do parts of, let's say, water, which is a compound, or parts of a scent, in there. And so it's not always an element by element breakdown of composition. Sometimes it's a compound by compound, especially with mixtures. It could be compound by compound. But even with substances, it could be a compound. That goes with hydrates. If we look at one of the hydrates we saw earlier, about half the mass of the hydrate was taken up by water. So there's like 50% by mass water incorporated into crystals. Did I show that already? You guys recall that? No? Maybe I don't have that. I'd have to go back to this. Yeah. And so calculate the mass percentage of fluorine in calcium fluoride. So did we already do this one? No. All right. Let's go ahead and do this one. So the first thing is, what is calcium fluoride? I think we did that, didn't we, or not?
No, we didn't.
No, we didn't. So what is calcium fluoride? The formula? CaF2. CaF2. That's good. So you're able to get it without, and that's because calcium's a 2+, fluoride's 1-. Only two of those balance out the chart. Calcium fluoride, CaF2. In CaF2 we have calcium, of course, and then we've got to get the mass for calcium. So let's take a look at the periodic table. That's where the mass is. Here.
For the average mass.
Yeah, we're going for the average. From now on, we're just going to go for the average. The only time we'd go for individual is if we're doing particulate, like say we're looking for single calcium. And even if we're going for a single calcium, I mean, which isotope are we talking about? Because calcium has multiple isotopes. And so let's take the average from now on, which is going to be 40.08.
78.0.
And then fluorine, we have 2 times 19.00. What is it?
78.08 is what we calculated.
Okay, 78.08. And this could be in grams, it could be in U, it could be in whatever. But the units are going to cancel out as long as they're the same. So if we do it like this, we'll do it just by grams because U, we aren't going to use that much. U would be the atomic mass units. We're mainly going to use grams. So normally when I think this is 40.08 grams per mole. And so the calcium, this is a mass percent, or M percent. It's just going to be, well, we have, not calcium. We don't want calcium, sorry, it's fluorine. The percent of fluorine is going to be, well, this is going to be 38.00. So we have 38.00 grams per mole of fluorine. divided by 78.08 grams per mole. Usually we just do 1 mole. 1 mole would be whatever, 78.08 grams. But anyway, the unit should cancel out times 100%. And that gives us what percentage by mass fluorine? So 38 divided by 78.08.
48.7%.
48.7. All right, how many sig figs are we allowed? 4. So
48.67.
48.67. Give me one more digit.
So there'd be 668.
668. Okay, let's do that. Is that 8 rounded or not rounded? Okay, that's good. And so then we show up rounding the rounding steps, which would be 48.67% fluorine. That's fluoride. And so, you know, when we look at the atom percentage, the atom percent it's going to be 67% fluorine, 2/3 fluorine, 1/3 calcium. But when we look at the mass percent, you know, fluorines don't weigh nearly as much. So it only comes out to about 49% fluorine by mass. .67%. So here they just did grams of fluorine. F. Why didn't they do F2? Isn't that what we have here? F2.
Is there only thing in one atom?
Well, it's because, you know, it's not an F2 molecule in there. These are 2 fluorine atoms, actually 2 fluorine ions. So that's why we only do F there, not F2. There could be 3 fluorine, it could be 1 fluorine. No. So this is grams of total fluorine. Calculate the percentage composition by mass of aluminum sulfate. Well, here we've got to calculate all the components. We don't, in this case, if it's this much fluorine, how much calcium?
51.
It'd be 100% minus this, because the rest is calcium, so it'd be about 51.33% calcium. Okay, but now we gotta do aluminum sulfate. That one's maybe a little bit harder. What's aluminum, the charge on aluminum? 3 plus, it's fixed. What's sulfate? Tell me the formula. Good. And so we have different choices. We have too much positive charge, so we'll up the negative. Now we have 3 plus, and the total of 2 is 4 minus. It's too much negative charge, so we'll go up positive. This is 6, it's 4. Now it's gone. So we'll need 2 aluminums and 3 sulfates. So that would be aluminum sulfate. Here. And so first off, let's calculate the total mass here. With 2 aluminums, and then we'll go to the periodic table, take a look at what aluminum is. What is it? It's going to be 2 times 26.98. And then how many sulfurs do we have? 3 sulfurs. This is going to be 3 times 32.07. And then we have how many oxygens? 12 oxygens. So we'll have to multiply by 3 down here. So 12, this is going to be 12 times 16.00. So let's go ahead and figure these out. 2 times 26.98 equals 5396. 3 times 3207. 3 times 3207 equals 9621. And 12 times 16 equals 192.00. Oh, actually, are we allowed that? Technically, we're not allowed that because of the 4 sig figs. But this is a failing of sig fig rules, actually. You know, the precision for the mass should have been to the nearest, because when you buy a balance, the cost of the balance depends on the precision. So if you buy a balance with 100 plate precision, it's going to cost you $500. If you buy a balance with 1,000 plates precision, it's going to cost you $1,000. And a tenth of, to the 10,000th, 1/10,000th place, it's going to cost you $5,000. So it depends on the precision of the balance. So anyway, if you leave it here, it's okay because, or you can take it out. You can follow the rules strictly, or you can leave it. Again, they're the rules. So. Did I do that right? 342.17.
Use the average?
Yeah, that's what we're gonna do, the average. We don't wanna do the individual because the individual, there's so many variations. You know, there are a lot of isotopes for all these. It's gonna get, how many different combinations can you have? But when you have 12 oxygens, you can have a huge number of combinations. So from now on, we're just gonna do the average. Uh-huh.
So, is that average for the whole ion compound?
Ionic compound? No, yeah, this is the mass
The mass?
of the whole,
Average mass?
yeah,
The whole thing?
the whole thing, the whole ion. This is how much one formula unit weighs 342.17 U or gram. U. And one formula unit would have 2 aluminum ions, 3 sulfur, and 12 oxygen altogether. 1 mole of those formula units, which would mean 2 Avogadro's numbers worth of aluminum, 3 Avogadro's numbers worth, or 3 moles of sulfur, 12 moles of oxygen, that's going to weigh 342.17 grams. So what we're going to do here is we're just going to continue here, and all we're going to do is we're going to divide it by this and then times it by 100%. Right? Divide by to get each component. And so we'll just do the first one. 53.96 is the mass of aluminum. So 53.96 divided by the total mass, 342.17 times 100. 15.769%. 15.769% aluminum. All right. Next one is 9621. So 96.21 divided by 342.17 times 100 would give us 28.117% sulfur. And then the last one here would be 192. 192 divided by 342.17, 56.112% oxygen. Now, these 3 make up the entire compound, and so if we were to add these up, let's see what it comes out to. It should come out to what? If we add these 3 up, it should come out to, well, 100%. So let's go ahead and do it. I'm going to add these up. it's gonna be 15,769 plus 28.117 plus 56.112, and I get 99.998%. I'm missing 0.002%. Is there some kind of contaminant in there? Some impurity? What just happened? Round off error. If I carried all the digits in the calculator, it would add up to 100%. And so this is due to round off error. So it's very close. When we round it, then it's going to round to 100%. For sure. They got 100%. Okay, we can use this. Remember we did the thing, like, we did the thing with the chlorinating solution. We could use that, like this. Aluminum chlorate is 38.35%. This is wrong. What is the formula for chlorate? ClO3 negative. Chlorate is ClO3 negative. And aluminum chlorate consists of aluminum ions and chlorate ions. What's the formula for aluminum chlorate? Al ClO3 3. This is aluminum chlorate here. It contains 38.35% chloride. What's the formula for chloride? Cl minus. Is this right? No. What did they mean here? They didn't mean chloride. They must have meant chlorine. It can't be chloride. You know, because the chlorate ion consists of chlorine atoms and oxygen atoms, right? But not chloride ions and oxide ions. If you think, okay, chlorate consists of chloride ions with oxide ions, how do those charges add up? Yeah, it comes out to -7. It's not correct. The chlorine atoms would carry kind of a high charge. What would the charge on chlorine be in chlorate? What would the charge on chlorine be in chlorate if I were to ascribe a charge to it? There's no way it's -1. It would be more like, well, 6, if this were +6 and these were -6, then chlorate should be 0 charge, because +6 and -6 perfectly balance each other out. It can't be +6, it has to be +5. And so this has got to be +5. It's not really an ion, like, for example, we don't call it the chlorine +5 ion. So sometimes what we do is we put a Roman numeral there saying that that's its apparent charge. And the apparent charge on chlorine is +5. Chlorine's not happy in the +5 state. You know, this is why we write the Roman numeral. Chlorine's not so happy. So chlorate is not so happy. That is, it's not so stable. You know? Chloride is stable. You know, table salt, chloride, is it stable? Yeah, but would you ever substitute some aluminum chlorate for your sodium chloride? Would you ever do something like that? No, because you can expect some nasty problems, yeah. Because chlorate is not happy. Is that mine? All right. Chlorate is not happy. It's because the chlorine's not so happy here. But anyway, this is getting aside. This is like little knowledge you're supposed to pick up. These little things you're supposed to pick up is like this. Tell me how you'd figure out chlorate is not happy, theoretically. You know, I don't want to memorize anything. I just want to know. Well, how would you figure that out? Well, I guess you could Google it, right? But that Google would just be memorized knowledge, you know, that's been archived. And so what we want to do is we want to pick up little things here and there. So just from looking at and then associating that, you know, because we associate, we try to associate what three things together. We try to associate, you know, properties with forms a little triangle. Maybe visually, but no. If I did this, you know.
Would the correct answer to that active exercise be this is impossible?
The correct answer would be 0. You can't.
Composition and structure.
Composition and structure. The correct answer, what mass of aluminum chloride? 0. You need something else, like sodium chloride, if you want chloride. Right? So what we're going to do is we're going to fix this. Well, how do we do this? How is this accomplished? This is accomplished by a combination of memorization and patterns and theory. So we got to start doing some memorization, otherwise you can't talk chemistry, basically. And so we start memorizing little things here and there as we go along. This is why, you know, that whole bit about repetition, this is repeated. So you've seen it. Now, if you've seen it before, oh, I've seen that before, then you recognize it. But anyway, we're going to fix this. It contains 38.35% chlorine. Okay, now that makes sense. There are chlorine atoms in chlorine. What mass of aluminum chloride is needed for 50.0 milligrams of chlorine? And so if I want 50.0 milligrams mg of chlorine, Cl atoms, pure chlorine, then what I'll know is that it's 38.35. So what does that percentage mean, 38.35? That means that we have 38.35 milligrams of chlorine for every 100 milligrams of what? Aluminum chloride. And so, you know, this is chlorine atoms. So we'll just put that in here. So we'll need 100 milligrams for every 38.35 milligrams of chlorine. Tell us how many milligrams we have. So to save some time, let's just see what they did here. So they wrote 130.37, that's good, and then they rounded it. So that's what I like to see. I'd like to see it before rounding and after rounding. So they rounded it to 1.30, that's where 3 sig figs. We got 4 sig figs in this one. Wait a minute, is this 4 sig figs or are these 3 sig figs? Let's convert it after. 4 sig figs or 3 sig figs? 4? Yeah. The answer is 4. You know, in exactly 100 milligrams of aluminum chlorate, there's approximately 38.35 milligrams of chlorine. Well, I'm going to skip this slide. We talked about empirical formulas. Can you remind me what the empirical formula is? empirical formulas are the, I know it's been a while since I typed. How long ago was it I
Simplest
typed?
whole number.
Yeah, simplest whole number. That was from week 1. Hopefully the stuff from week 1's like kindergarten. You know that stuff from kindergarten? Hopefully it's like that now because, you know, you've seen it so many times, right? Hopefully. But can you imagine having to go back to kindergarten? That would be quite torturous because, you know, you've seen that type of stuff over and over, like the ABCs, right? That kind of thing. You know. And then you would know, you know, when that's always a satisfying feeling because, you know, quarter system is so fast. It's in 10 weeks, you know, 10 weeks and then you have your final exams. So by the time you hit the 10th week, the stuff from the earlier weeks should be pretty easy by then, you know, really basic. And that's always a satisfying feeling. But if the stuff from the beginning of class is still challenging, then you got some trouble ahead, you know, possibly. But anyway, let's get back to that. Simplest whole number. Is this an empirical formula?
No.
No. This is what we call molecular formula because the actual molecule consists of 4 carbons. 4 carbons is called what? When we have 4 carbons, it's called Oh, tetra? Oh, no. Yeah, that's right. Actually, this would be called tetracarbon decahydride. That would be our standard, but that's overridden by another set of nomenclature rules. The other set of nomenclature rules are called the organic nomenclature rules for hydrocarbons. So when we're dealing with hydrocarbons, compounds that consist just of hydrogen and carbon, we have a new set of rules, and we don't use the other set of rules I told you. And the new set of rules is this is called butane. Butane. And so unfortunately, there are too many rules. This is why organic chemistry kills a lot of students because of the nomenclature rules. A lot of students have trouble memorizing all the rules and all the ways to name it. No, it's easy. I didn't think organic was all that hard because I really spent a lot of time learning the nomenclature rules. But that required a lot of memorization up front. And now some of my fellow students, they didn't want to memorize things. I didn't understand it. And so they couldn't name basic ones like this. Butane. But, you know, how do I know? Well, what is the empirical formula for butane? It would be C2H5. C2H5. So that's not that hard. So this we call a molecular formula. This is empirical formula. Empirical formula, what's better to know? The empirical formula or the molecular formula? No, the molecular. You know, if you're only given the empirical formula, how in the heck can you tell that's butane? You can't really tell, can you? You know, you need the molecular. And so, you know, we only use empirical formulas for the things that do not form molecules. For things that do form molecules, we need to use the molecular formula. However, if we have an unknown molecule and we send it out for, you know, we want to figure out what that unknown molecule's composition is because we need to know the composition to correlate it with the properties, right, and then figure out the structure. If we have an unknown molecule and we want to figure out its composition, then we're stuck. We have to first get the empirical formula, which isn't as useful, and then figure out the molecular formula from that. And so even for molecular compounds, we still end up determining the empirical formula because from chemical analysis, did I talk about that yesterday? Chemical analysis? From chemical analysis, what do we get? If I send out a sample, what do we get? Do we get the formula? What's that? Yeah, we get the percentage for each element by mass. Yeah. Unfortunately, we don't get the atom percentages or atom ratios. That would make it easy because formula is just the atom ratio, or atom percentage, atom fraction, whatever. But instead we get the mass. And so we sent out a sample for chemical analysis. And then we have to follow a certain set of procedures. So I'm going to skip this slide. How do we determine an empirical formula? Send out a sample. And the sample, let's say it's a pure compound. If it's a mixture, then it's okay. We could send out a mixture, but still don't know what the components of that mixture are. So it's best to send out a pure compound. Compound would be what? Two or more elements combined. Or it could be an element. An element that will only have one thing. But anyway, it contained 1.61 grams of phosphorus and 2.98 grams of fluorine. And so you send out this sample, and that's what they determine, because that's what their instruments do. And they don't want to do any calculations for you. They just want to give you the data, right? And so here we send out our sample. This is an unknown sample. Send out the unknown sample. The unknown sample comes back from analysis. Containing 1.61 grams of phosphorus and 2.98 grams of fluorine. Should I write F or F2? F or F2? F2? This F2, do you know what F2 looks like? Yeah. But do you know what it looks like? Do you know what chlorine gas looks like? Have you ever seen chlorine gas? It's yellow gas. Yeah. So what do you think F2 is? Gas, liquid, or solid? It's a gas. This is what it looks like. And so this unknown compound's a mixture then. If this compound's a mixture, then it contains solid phosphorus, which we had white phosphorus or yellow phosphorus, and this kind of yellow-green fluorine gas. It's a mixture? Or is it a compound?
Compound.
It's a compound. If it's a compound, then it's not F2. It's just F atoms incorporated in there. So it would not be F2. F2 is definitely the element fluorine, which looks like that.
So F is just the atoms?
The atoms. And so we have lots of, it could be PF, it could be PF2, it could be PF3, it could be PF4, PF5, PF, could it be PF6? It could be P2F, right? Etc. I don't know what it is. Yeah, it's going to be fluorine atoms incorporated with phosphorus atoms in a compound. So, for example, if I look at water, this H2 is the element hydrogen, the clear colorless gas.
No.
So H2 consists of H2 molecules and an oxygen atom, or does it consist of H atoms and an oxygen atom? H atoms and an oxygen. There's no H2 molecule in it. So this is why. And so what we're going to do is we're going to get the empirical formula. And so what we need to do is, what is the total mass of this compound? So what is the total mass of this compound?
4.
Well, that's going to be 4.59 grams. And so the total sample weight is 4.59 grams of the sample here. Just calculate that. And what we're going to do first is we're going to figure out the percent phosphorus. So let's figure out the percent phosphorus. How would I set it up? percent phosphorus is equal to 161 divided by 4.59. The units have to be the same, grams, grams.
Yeah.
So cancels times 100%. And what does that come out to? $35.076. 35.076% phosphorus. Actually, I'm only allowed 3 sig figs, so let's just go 35.07% phosphorus. And then fluorine, it's going to be equal to 2.98 divided by 459 times 100%. 64.9. We're going to go with 3.
Okay.
Because the other way we could do this is, these have to add up to 100%. So I just take this minus 100%. But actually, it's probably 2. If I actually did the calculation. All right. That's the percent. Now what we're going to do is this. This is a standard procedure. To determine the empirical formula, what we're going to do is a certain number of steps. To determine the empirical formula, step 1 is we assume a 100-gram sample. This is from percent composition. Assume 100-gram sample. If I have 100 grams, how many grams of phosphorus in this?
Phosphorus 35.
Yeah, therefore it should be 35.07 grams of phosphorus. And how many grams of fluorine?
64.92 grams of fluorine.
Yeah. Good. All right, 2. Are formulas at mass ratios or formulas atom ratios or mole ratio?
Mass ratio.
So what's the formula for water in terms of a mass ratio? In terms of mass ratio, it's like this: H11O89. So formulas are not mass ratios. Formulas are atom ratios. But atom ratios can also be called dozens of atom ratios or moles of atoms ratios. And so what we're going to do is formulas are mole ratios. And so if I have a 1 mole of water, then I have 2 moles of hydrogen atoms and 1 mole of oxygen. So this is a mole ratio. It's not a mass ratio. And so what I'm going to do is I'm just going to convert to moles. Convert to moles. And so phosphorus, we divided by 32. Oh, what is phosphorus? 30 point. Oh, sure, I can move on right here. 30.97. In other words, I'm just going to times it. 1 mole of phosphorus is for 30.97 grams. Now phosphorus is very interesting because phosphorus only has 1 isotope. What isotope is it? P30 or P31? P31. There's only 1 isotope of phosphorus, P31. Naturally occurring. They're radioactive isotopes that occur for phosphorus. Phosphorus is very important. Why is phosphorus very important? For life. Phosphorus is very important for living. And so all the biochemists use radioactive phosphorus. Fortunately, it wasn't too nasty, but they all used radioactive phosphorus as tracers. They wanted to follow the phosphorus around the body. How was it metabolized? Where did it end up? And so it's easy because if you mark some molecules radioactive, then you can just follow them. You know, they end up here. Kind of thing. But they didn't use P31. They used something else. Fluorine's pretty interesting too because fluorine only has how many isotopes? One. It's fluorine 19. Okay, so how many moles does this work out to here for each? So it's going to be 35.07 divided by 30.97. 1.132. 1.132 moles of phosphorus. Then how many moles of fluorine do we have? 64.92 divided by 19. 3.416 moles of fluorine. And then the formula is a mole ratio, right? So we'll just take the mole ratio. It's going to be P 1.132 F 3.416. Now, name it for me.
It should be whole.
It should be whole numbers, right? This is not whole numbers. And so maybe this is totally wrong, or is it totally wrong?
Or not even sure all
No, it's not totally wrong. 3. Get the mole ratio. Okay, and then 4. Simplify. Get simplest whole number ratio, which is called the empirical formula, whole number ratio. Well, how do I get the simplest whole number ratio from this? What we do is we just divide it by the smallest number. So what we'll do is we'll just do 1.132 divided by 1.132 here. And then F is going to be 3.416 divided by 1.132. And so that's going to come out to P 1.000 F. Let's go ahead and figure out what that is. 3.416. 3.416 divided by 1.132 equals 3.01. 3.017. Ooh. How would you name that? Phosphorus. Almost tri, but not quite. So it's tri 0.017? No, what do you think happened here? Either rounding or experimental, you know, some experimental errors. Most likely it's PF3. And so what we'll do is we'll just round it. PF3. Now how would we name that? We'd name that phosphorus trifluoride, but we don't know, you know, because this is the empirical formula. We don't know if it's really phosphorus trifluoride because it might be diphosphorus. What's this called? Diphosphorus hexafluoride. Or it might be triphosphorus nonafluoride. Or it might be tetraphosphorus ran out of prefixes, so maybe we'll skip those ones down here. They're too complicated. No, it's not. Actually, there are names. You know what? 12. They have names. Like 22 has a name. I forgot the name though. I used to know the name for 22. Ico. It's Ico. Icos. But whatever, etc. And so this is the empirical formula. But which of these is the molecular formula? You know, we don't know how big the molecule is. Right? And so all we're getting from this is the empirical formula. Is the empirical formula or the molecular formula more useful?
Molecular.
The molecular formula is much more useful. And so how the heck can we get the molecular formula? Okay, so we have the empirical formula here. PF3. Well, it depends. If it is a ionic lattice, is there such thing as a molecular formula? No. If it's a covalent lattice, is there such thing as a molecular formula? It's only if it's a molecular compound. So maybe we don't need the molecular formula because this might not form molecules. But when you look at it, you can tell right off that this is going to form molecules. Why? Two nonmetals. Binary compounds. These are called binary molecular compounds. This is molecular. And so I expect this to form molecules. So we'll stop. Now, can you figure out a way to determine this? The way to determine this is this. Let me do this as an extra step now. To determine molecular formula, which is going to be a heck of a lot more useful, is feed molecules of the unknown into what? You know, all we do is we take some molecules and then feed them into a machine. What machine would you consider feeding molecules of this into? A machine based on the cathode ray tube concept. Yeah, it's not a CRT, but it's kind of similar to a CRT. What machine was that?
The laser one?
Well, there's a laser. It could be a laser, but you don't need a laser. I mean, if it's already a gas. This one we wouldn't need a laser. This one we wouldn't need a laser because PF3 is, you don't need to blast it apart. You need the laser when things are kind of hard to break apart. The PF3 is easy. A machine that has a big magnet in there. Vacuum, all that other stuff. MRI has a gigantic magnet. Yeah, you're right, but it's not an MRI. M is right, it starts with an M, but MRI is not right. Well, we wouldn't say high pressure because the vacuum's the opposite. Vacuums are low pressure, very low pressure. High vacuum, yeah. Ultra high vacuum would be very, very low pressure.
The one you showed us a picture of?
I showed you a picture of the machine.
The one looked like microwave.
It looked like a microwave oven, yeah. What was that called? Mass spectrometer. Yeah. So we feed molecules of the unknown into a mass spectrometer. Well, what can we do with a mass spectrometer? We could weigh atoms, and if you're gentle enough, you could weigh molecules. And so if we weigh a molecule, then we can figure it out because these molecules weigh different amounts. For example, PF3 weighs 60, about 60 U. about 60 U. P2F6 would weigh about 120 U. This would weigh about 180 U. And this one would weigh about 240 U. And so if we can take a molecule and weigh it, then we can see how big the molecule is. The bigger the molecule, the more heavy it is. The smaller the molecule, the lighter it is, right? And so we feed these molecules into mass spectrometer. If they break apart, it's okay, but they fragment, but we can put it back together based on the fragmentation pattern. This is why we don't want to hit this with a laser, because it's going to tear everything apart. We're just going to have atoms, you know. And so if we're gentle, we can weigh it. And so when you're gentle, you don't use electron gun. You use something like chemical beam. It's called. You shoot molecules, soft molecules at the target, and this kind of stuff and that kind of stuff. And so we feed this in, and then the mass, the molecular. What should we call this? Molecular mass or molar mass? The molecular mass comes out to about 60 U. The molar mass would be about 60 grams per mole, but we don't weigh a mole of this stuff. We just weigh individual molecules. But you know, I'm saying about 60 U because when we do this, are we going to find a molecule that weighs exactly 60 U? No, because of what are those things called? The atoms that weigh different amounts. Isotopes. Because of isotopes, we're going to get a lot of different isotopes, and we're going to have different masses depending on which molecule we're looking at. And how many different PF3 molecules are there? Well, actually, this one's very interesting because this one. This one, yeah, it doesn't have, because phosphorus is 100% and fluorine is 100%. So this pattern's going to look very simple because there's only going to be one mass. However, with something like water, how many peaks would we have for water? 9. You know, 9 different peaks, 9 different weights. So it gets more complicated, but this one's quite simple. It's kind of interesting. And so when we weigh it, you know, the molecular mass is about 60 U from experiment. Therefore, the molecule must be PF3. Therefore, the molecular formula is PF3, which we call, what do we call this? We call this phosphorus. Phosphorus trichloride.